everyone, I am Haiying Che from Institute of Data Science and Knowledge Engineering, School of Computer Science, in Beijing Institute of Technology. In this session, we discuss in-memory database. From the perspective of computing architecture, the data processing system is divided into data algorithm layer, computing model layer, computing platform and engine layer, etc. Computing models are the way that different kind of big data is processed in different scenarios. We have learned the batch processing, stream computing, large-scale concurrent processing model for structured data. And in this session, we discuss in-memory database. There have been multiple advances in industry in both hardware and software architecture, which makes memory-based computing more feasible today than in the past, as outlined in the diagram below. In a nutshell, the availability of new classes of hardware with the support of 64-bit CPU can now support 2 TB on a single device. In addition, the advances in software architecture and solutions towards distributed architecture and cloud make it easier to utilize these new hardware capabilities. In-memory computing, in many ways, in-memory computing is a close relative of in-memory database. As with many databases, it was designed to enable all the data management aspects that are often expected from a traditional database, such as queries and transactions, with the difference that the data is managed on RAM devices and not a disk, and thus comes with potentially 1,000 times better performance and latency according to various benchmarks. The main differences between the traditional in-memory database and in-memory database computing are that in-memory computing is designed for distributed and elastic environment. In-memory computing designed for in-memory data processing. HANA combines the hardware advantages and software advantages to make the in-memory database possible. The development of the hardware technology, multi-core architecture, parallel scaling across blades, 64 address space, 2 TB in current server board, 25 GB per second data throughput. All this made the cost-performance ratio rapidly declining, which means the advanced speed processing hardware become cheaper and affordable. HANA database also include some advanced software technology and special methods, which include combining row-based and column-based store, compression, partitioning, no aggregation tables, insert only, and on-the-fly extensibility. We will explain this one by one. The first one, row-based store, is designed to support transactions processing, OLTP, online transaction processing, and the column-based store is support analysis processing such as OLAP, online analysis processing. Secondly, because the memory size cannot be as big as the hard disk, we must try any method to reduce the size of the database. HANA used a lot of compression methods. The third one, in order to increase the database performance, the database can be partitioned to achieve the parallelization and improve the performance. The fourth aspect, for eliminating the aggregation tables, normally for data analysis, The data warehouse is built to collect the relevant tables data from multiple data sources and get some aggregations to facilitate the further analysis. But in HANA, it doesn't need the aggregation table. The aggregation in memory can be done quickly. No need to do it in advance. On-the-fly aggregation performance will not be affected, and the aggregation table made the redundant data which cost the memory space. The fifth, and what are the benefits of the insert-only approach? Well, since the main store is compressed, which is good for reading performance, changes would be expensive. Just imagine you want to make a change in a compressed text file. You need to uncompress, make the change, and compress again. For this reason, data is only appended to the unpressed data store, while change operations are much cheaper. The merge moves the data from delta to main and thus compress only from time to time and not with every change. Setting the deleting flag is based on row IDs and works for compressed and uncompressed data. In the column store, HANA will only insert data. That is, whenever you update or delete data, HANA will just insert. For performance reason, the column store is divided in a main and a delta part. New data is going to the delta and will be merged frequently to the main. Changing statements work as follows. First, insert. An insert statement will just insert a new record in the delta. The merge process will move the record from delta to main. Delete. A delete statement will select the record and mark it as invalid by setting a flag for main or for delta. The merge process will delete the record from memory once there is no open transaction active for it anymore. Update. An update statement will insert a new version of record. The merge process will move the latest version from delta to main. Old versions will be deleted once there is no open transaction active for them anymore. The update, therefore, consists internally of an insert plus delete. The following picture illustrates this principle schematically. Please note that this picture does not reflect the real storage in column store. You can see a deleted record in main, ID 7, and two old versions marked in gray of record, ID 8 and 14, while the name has been updated, which leads to an insert of a new version of the records. The fifth aspect. HANA is an in-memory database, but what exactly do we mean by that? Don't all databases use memory? Yes, but with a big difference. Other databases store data in physical pages on hard drives and move copies of some of the data into memory. This is called caching. When data is missing from the memory cache, it must be fetched from the disk, which takes a very long time, with a minimum latency of 10,000 microseconds, holding up the queries and calculations. Not only that, since the data in memory is a copy of the disk, it is stored in a way to reflect the disk structure in the form of linked pages, sectors, etc., which adds additional overhead when fetching the data. HANA, on the other hand, stores the data directly in memory, optimized not for how the data is stored on disk, but optimized for efficient access, and as we shall see, highly compressed using the most efficient memory representations that computer scientists can come up with. Even in the event of a cache miss, it only takes 0.1 microseconds to fetch the missing data from DRAM, DRAM. That is 100,000 times faster, and this makes all the difference. Note that when a transaction changes a piece of the data, HANA logs a record of that change so that it can be recovered in the event of a crash. The sixth, there have been two industry trends that enable HANA performance. The first trend is the astonishing way that memory prices have gone low in the past several years. What was unimaginable only a few years ago has become totally affordable today. As you can see from this graph, which shows the price of a gigabyte of RAM over time. Notice how little time it took for a 10 times reduction from $100 per gigabyte to $10 per gigabyte. Today, a terabyte of memory costs much less than $10,000, and computer makers are now putting together servers with 4 and soon up to 12 terabytes of memory in a single system. The seventh aspect, the second trend, is the way compute power has gone up. A little over a decade ago, we would buy a computer with a single processor. Then, several years later, Intel introduced dual-core processors, followed not long ago with 64-bit processors with 8 dual-threaded cores. The first server for HANA would have as many as 4 such processors. Now we are seeing Intel Sandy Bridge processors with 12 cores and servers with up to 16 processors. That is not just a 200 times performance jump in a decade. This really heralds a challenge for modern software. In memory now also means that the software must be written to leverage the multi-core architecture of modern processors and multiprocessors server and even scale out beyond. Disk-centric computing is also a major factor that forces separation of transactional and analytical workloads. Specialized data warehouse for reporting and analytics required the moving, transaction, and pre-processing of transactional data. These introduce a huge complexity. Sometimes an enterprise may hold 3 different copies of the same data. Leveraging the power of in-memory computing allows HANA to bring OLTP, transaction processing, and OLAP, data process, and OLAP, data analytics, back together in one database. HANA reverses the industry trend for separated, specialized analytic database. The result is a significant landscape simplification. This image is a simplified architectural picture of SAP HANA. HANA is certified and delivered on powerful enterprise servers from partners like IBM, HP, Fujitsu, Cisco, Dell, and others. These highly optimized servers scale up to 192 cores and managed by Linux operating system from partners like SUSE and Red Hat. The HANA software is carefully optimized for the hardware it runs on. and takes advantage of the massive parallelism and memory architecture of the modern processing cores on which it runs. A variety of storage systems can be used for high availability and backup support, including solid-state or flash disk. HANA is fully compatible with other database systems and supports SQL, JDBC, ODBC, and analytical data source interface, like MDX multi-dimensional expressions. This means that existing applications can use HANA without any modifications. In addition, HANA supports web-based interface, which we will discuss later. HANA was designed from the ground up to be massively parallel at every level of operation. One of the main reasons why it performs so well. The first level is simple. Multiple concurrent users and queries are allocated their separate compute resource. The HANA optimizer then creates an execution plan that parallels the operations within a query. For instance, I can scan 2 columns at the same time on different processing cores. And by partitioning the data, I can parallelize such operations even more, even over multiple servers. For instance, I can sum table A over as 4 separate concurrent aggregations, and finally sum the 4 results together. And by using processor techniques like hyper-threading, we get even more concurrency. And all of that is internal to HANA. The applications are not aware of this, except that they enjoy better performance. Here is another very important attribute of HANA, the way that data is stored in memory. Traditionally, databases store data in rows. One reason is that this is much more convenient when the database is stored on a disk. You simply write a new row to the end of the file. HANA, on the other hand, stores its tables in columnar order. This means that it is much more efficient to perform an aggregation, sum of cells, for instance, because all the relevant data is in consecutive memory locations, and most values will be pre-fetched by the processor. Not only this, but by storing data in columns like this, we can sort and compress it much more efficient than with conventional database. In traditional database, it is often impossible to perform data analytics on the raw, original transaction data. Therefore, modeling experts are forced to introduce extra tables with pre-calculated summations, average, etc., to increase analytic performance, giving up detail. For instance, we could sum sales by country in the table above, resulting in another, smaller table, which is faster to access for generating reports. These extra tables are called materialized aggregations. The trouble with these aggregations is that they make applications very complicated. Every transaction also requires the subsequent recalculation and updating of all affected aggregation tables, which may slow operations down significantly. Another approach, updating the aggregates periodically, means that reports are often not up to date or don't match the transaction data. But HANA can aggregate massive data sets with high performance, over 15 million aggregations per second per core. This immediately yields simpler data models with fewer tables, no loss of detail, much simpler application logic with much fewer write locks and logs, better up-to-dateness. All of this improves the performance dramatically. This is one of the reasons why customers report hundreds of times of performance improvements. Business intelligence and data analytics often use normalized data models, referred to as star schema. This involves holding all the fact data in one large table, with reference to other information in separate table called dimensions. For instance, we could have all our sale data in the central fact table and the details like country and product in mention tables. HANA has a specially optimized execution engine for this type of model, which often speeds up operations on such tables 10 times or more and contributes greatly to the overall performance impact of HANA. Scanning column data is so fast that a lot of index are usually not required. HANA by default only indexes the primary key. This saves memory as well as index update time. Dynamic views can be computed on the fly at over 1 billion records per second. Aggregations are very fast as well. And you can see how it is easy to change the table. For instance, to add a new column without complete table reorganization. Each column is managed separately. And of course, looking only at some of the column, an operation called projection, is trivial in a column-oriented database. Compression reduces main memory access. This doesn't only represent a performance bonus due to improved cache behavior, but illustrates another advantage of an in-memory database. The same amount of memory holds a lot more data. It is not uncommon to see a data compression ratio of 5 times. In this session, we learned the in-memory database HANA, which applied the advanced hardware technology and developed software technology. Thank you for your attention. If you have any question, feel free to contact me.